My name is Rudra Kumaran Anandikimanavaran. So let me do the introduction. In aerospace engineering, reducing the weight of the aircraft component is critical. It improves the fuel efficiency, reduce emissions, and enhance performance. One such component in the engine bracket which support the engine cooling during maintenance. So in this project, we we aim to redesign the bracket using the alternative methods for focusing on reducing the mass, sufficient strength, and with less deformation and avoid resonance vibration. So we used computer-aided design, which is a CATIA. We use a CAD and ANSYS workbench for engineering simulation to analyze the different material brackets designed under static, thermal, and vibrational conditions. Our goal is to find a sustainable, efficient, and structurally safe design while promoting resources optimization and environmental goals.
Uh, Good evening, everyone. My name is Vishwam Son of Murgaya. I am from class product design. So I would like to start my presentation with methodology. So there are three main parts in methodology, which are linear static analysis, thermal stress analysis, and free vibration analysis. Before the three main parts, we do the bracket in CATIA V5. We also apply material aluminum to bracket at CATIA V5 to see the density and also the mass before we proceed to NC software. So after that we save the CAD part in IGS format to use the bracket in NC's later. So now we move to linear static analysis. So in engineering data, we put the material aluminum 606.6, and after that we will put the values of density, Young's modulus, Poisson ratio, and tensile yield strength. So after that, after we do the geometry, so we double click the model to do the linear static analysis. So we create material assignment of aluminum 606.6, and we also insert mesh, which is tetrahedrons with element size 3.0 millimeters. After that, we put the fixed support at the four holes at the horizontal part of bracket. So each hole has two surfaces. So there are a total of 8 surfaces for fixed support. After that loads, so we put the load at the hole of loading area. So there are 4 surfaces in my design. So there are 4 surfaces at the loads. So after we apply the load, we change the vector to component and we put the 60,500 Newton load in Z component. So after that we move to solution. So we add the total deformation and FOS to solution and solve it. So after we get the results of linear static analysis, so we go to thermal stress analysis. So thermal stress analysis almost same as linear static analysis. So we duplicate the linear static analysis at the NC software. After that, we add the engineering data, which is isotropic instantaneous coefficient of thermal expansion. So after we edit the engineering data, so the procedures are almost same as a linear static analysis. So we do enter the loads. After that, we change the environment temperature to 25 degrees Celsius. So we also add thermal condition. So we put the final temperature for bracket 125 degrees Celsius. After that, add solution. So we add equivalent 1 meter stress, total deformation, and factor of safety. So after we get the results of thermal stress analysis, so we move to free vibration analysis. So for free vibration analysis, we use the tool model in NC software. So after we do create material assignment and fix support, so we directly move to solution uh, by right clicking the solution and click the solve. So there are 6 type of total deformation. in the results. So we record all the results. Let's move to results. So this is the results of linear static analysis. The picture above shows the results of rotor deformation, and then the picture below shows the results of safety factor. So this design applied material aluminium 6061T6. It, it, it has mass 0.54449 kg, FOS 1.4432, which is minimal, and maximum total deformation is 0.22713 millimeters. So this result shows that this design has fulfilled the design requirements, which is mass must be less than 0.8 kg, FOS must be between 1.2 and 3, and maximum total deformation must be less than 0.35 millimeters. So the picture below shows the results of thermal stress analysis, which are safety factor, equivalent one missile stress, and total deformation. So the maximum equivalent one missile stress is 807.39 MPa. The minimum safety factor is 1.4432, which is almost same as the result of linear static analysis, and the maximum total deformation is 0.31877 millimeter, which is still less than 0.35 millimeters. So this table shows the results of free vibration analysis of the design model. So there are six types of deformation results, which are simple bending, transverse bending, bending at bending at mid, transverse bending, bending at middle span, twisting, bending at quarter span at mode 6. All the six natural frequencies are significantly higher than the engine excitation frequency, which is 275.8 Hz. Therefore, the bracket is not at risk of resonance, and it is structurally safe from dynamic vibration amplification under engine operating condition. This wide frequency separation is ideal. It means the bracket has been designed with sufficient stiffness and appropriate mass distribution. So that's all from me. Thank you.
So, as for the discussion, our final design, known as Design 4, was optimized for minimal mass without compromising strength, and we chose aluminum 6061 T6 due to its excellent strength to weight ratio, corrosion resistance, and lower environmental impact compared to titanium. The final mass of our final design was 0.544 kg. Well, it's below the 0.5 kg which was our target. And the space safety factor was 1.44, which is more than 1, safely within the required ranges 1.2 to 3.0. And the maximum deformation for 0.227 mm, which is also safety below the 0.355 millimeter limit. So we achieve all the three important things. The factor of the safety, or the FRS, play a key role. With a value of 1.44, it shows that the bracket can handle 44% more stress than the applied 6,500 Newton load. This means no risk of yielding of plastic deformation. We also observe that the bond misses stress, the stress stayed below the material's yield strength due to the good stress distribution. The optimal geometry, particularly the ribs and fillets, help minimize the stress concentration and improve speed. As for the thermal stress analysis, we simulated the bracket being exposed to a high temperature, rising from 25 degree to under 25 degree, just like what the temperature difference in a real engine, which is on more than 100 degree. So these thermal conditions effects the the stress jumped to 807 megapascal, which far exceeds the aluminium yield strength of 276 megapascal. The FIS dropped to just 0.34, which is below 1, near to 1, so it's more prone to failure. Deformation increased from 0.227 millimeter to 0.318 millimeter, still under the limit but showing address state. This shows a serious vulnerability to thermal loading. The problem arises from the resistant thermal expansion. The brackets want to expand with heat, but the fixed support don't allow it. So the internal stresses build up. In summary, while aluminum 6066 is excellent in normal conditions, it's not the ideal thermal environment. Future designs we suggest using material like ILVA or adding feature like expansion joints or thermal bed. So the field vibration analysis identify the first 6 natural frequencies of the bracket. All of them range between 0.9 to 9.4 kHz, while the engine's expecting frequency is just 275.8 Hz. That's a huge gap, which means there's less risk of present. This proves that our design has a sufficient stiffness and proper mass distributions to avoid dynamic vibration issues. Still, we suggest adding a damping pads as an extra safety measure to observe high frequency vibration during engine operations. So, design 4 with aluminum 606 T6 met all static criteria and performed best structurally. Thermal performance was a major weakness. Stress exceed yield strength under heat. The vibration performance excellent and natural frequencies are far from engine frequency. So for the recommendations, we recommend 3 improvement going forward. Use low expansion alloy or redesign support to accommodate thermal expansion. Add ribs or fillet at a stress-prone zones to further reduce concentrations. Explore composites material like carbon fiber for better thermal performance and lightweight. Conclusion: linear static analysis show our design was 73% lighter and have a higher FRS and lower deformation compared to the original. All design goals were met, but thermal stress analysis revealed that the design failed under high heat. Free vibration confirmed that the bracket is dynamically safe, no resonance risk. Finally, 3.0 mm mesh may have missed finer stress details. Material properties were assumed constant, temperature-dependent behavior was not included. Real-world constraints may differ from our fixed support by. For future work, research is conducting convergence studies, temperature dependence, material simulations, and validating our results to physical testing. Overall, this project succeeded in meeting the goal lightweight design, safety, and efficient material use, aligning with SDG 12, responsible consumption production. Thank you.